Hi, good greetings. So today we will continue with chapter 5, part 1. We will be covering three-phase system. Okay, so electrical power is generated, transmitted, and distributed in the form of three-phase power. It's not single phase or double phase. So usually it will be sent in three phase. So as you can see, so the differences between three-phase line. So usually you will have three or four lines, so depends. And this is single phase line, which only having one or two line. So one is the electrical line and also the neutral. Okay, why three phase power is preferred? Because three phase power motors, generators, and transformers are simpler, cheaper, and more efficient. Okay, because we want to have a continuous power. So we must have a system which can provide us continuous electricity in a simple, cheaper, and more efficient way. Okay, so three-phase transmission line can deliver more power because it has more capacity, uh, and considering the weight and also the cost, so this will be much better. And the voltage regulation of three-phase transmission line is inherently better compared to single and double phase. Okay, so today we will see single phase, double phase, and also triple phase and generators. Okay, so consider a permanent magnet NS. So the magnet, yes, we know it has two poles, so north and also south. Okay, so we will have this in a generator. Okay, we will have a stator and also the winding. Okay, so winding will have terminals. So like here, so it's a coupling A and A and one. So we call it as a winding A1. Okay, so if we have more windings, so it will be called accordingly. So consider a permanent magnet NS revolving at constant speed inside the stationary iron ring. So we have a stationary iron ring, and the magnet is rotating inside. The magnet is driven by an external mechanical source, so usually will be turbine or motors. Case or multi-turn rectangular coil having terminal A1 is mounted inside the ring but insulated from it. So you have a terminal A1, so it's mounted inside the ring. Okay, so we can see, so this is a permanent magnet. Okay, when the magnet turns, it sweep across the conductor inducing a voltage. So you have a winding, you have a conductors around, and when the magnet rotates or move, so it will cut the magnetic flux, and because of that, a voltage is induced. So the voltage induced EA1 equals to BLV. So EA1 is the instantaneous voltage induced. Okay, B is the B field. Okay, instantaneous flux density cutting across the conductor. So it's inside B field. We call it as a B field. L is the length of the conductor. So the length of the conductor attached to the stator, and V is the peripheral speed of the revolving poles. So we have two poles. So how fast it moves and rotate. So we will take into consideration. So the voltage induced in winding. So let's say we call it as a winding A. Okay, so the sum of the voltage induced in all the conductors appear across the terminal. The terminal voltage E1 is maximum when the poles are in the position A. So we can see this is A. So when the magnet is straight to the terminals A1, it will generate a maximum power. So if you see the graph, So this is a graph of angle versus voltage generated. So it will be maximum when the position is like this, and it will be minimum or zero. Okay, it will be zero when this is far from or in the opposite direction like this. Okay, so it will be far from the poles, so from the windings. The voltage is zero when the poles are in the different position B. Okay, the alternating voltage has the peak value of 20. Okay, 20. Machines that produce such voltage are called alternating current generators or synchronous generators. Okay, so the power, we will see the power output. The power output of a single phase generator. So when you only have two windings A1, so we it's only having single phase. So that's why it's only having one set of wires. Okay, so we call it as phase A. So resistor is connected across terminal A1 and A. So the resistor is connected. So you have a resistor here. So there's a wire here and also wire here. And the current will flow and the resistor will eat up. So when the resistor eat up, it will add the load to the phase A. Okay, so you can see the current IA. So we have a current IA here is in phase with the voltage because voltage the curve is like this. So it is in phase because when it goes down, it goes down, and when it reaches zero, it reaches zero also. So we call it as a both are in phase with the voltage. Current is in phase with the voltage, and the instantaneous power is composed of a series of positive pulses. You can see. So this is the power. So when the power is generated, so usually it will be positive. Okay, so negative power is indicating a different direction. So the electrical power is derived from the mechanical power provided by the turbine driving the generator. So electrical power is from the mechanical power. It is transferred or changed to electrical power. Here the mechanical power is provided by the turbine, which is rotating the magnet, and the electrical power is derived from the whole setup of the power generator. Okay, so that is for a single phase generator. So now we will see double phase generator or two phase generator, as we can see here. So we can see the setup itself. So earlier we only had A and 1. So now we have additional B and 2. Okay, so this set we call it as winding A, and this set is called winding B. Okay, we'll see some example explanation. A single generator is one second winding on the stator identical to winding A. So like this, as the magnet rotates, sinusoidal voltage are induced in each winding. So earlier we can see when it's like this, the magnet is in this position. So this will be the maximum. And when it rotates, when it the magnet become like this, magnet become like this. So uh, B2 will be winding B will be maximum. So what it will do? So it will produce two signals. So it will produce two signals of same magnitude, same value and frequency, but not reaching at the same time. So you can see here is maximum, and when it come here, so the second one is maximum. So when it goes continuously, so it will produce a very stable stable power. Okay, so voltage EA1 passes through its maximum positive value. Okay, maximum positive value. So when its maximum positive value, we can see EB2 is 0. Okay. After a rotor has made a quarter turn 90 degrees, so like here, so from here to here, so then we can see it will become straight like this. So voltage E1 becomes 0. Okay, so when it become like this, so E1 will become 0. So we can see the EB2 become maximum. So this is called two-phase generator. So in the two-phase generator, two signals are generated and it will appear at different time. Okay, so we can see one example. So the generator shown in figure rotates at 6,000 revolution per minute and generates an effective voltage of 170 voltage per winding. So determine the peak value across each phase, output frequency and also time interval corresponding to the phase angle of 90 degrees. Okay, so how to calculate the peak voltage? So to calculate the peak voltage per phase, we have two phase. So we want to calculate per phase. So EM equals to square root of 2E. This is from the previous chapters. So square root of 2 is 1.414 times with E is 170. Okay, so is equals to 240 volt. Okay, so one cycle is completed every time the magnet makes one turn. So the period of one cycle is, so it is given revolution 6,000 revolution per minute. So we want to convert it into seconds. So T is 1 over 6,000 minutes. Okay, so 1 over 6,000 minutes. So 1 minute it has 60 seconds. So 60 divided by 6,000 second is 0.01 seconds. So which is 10 milliseconds. So we know the frequency is 1 over T. So F is 1 over T. So 1 over 0.01 is 100 hertz. Okay, the unit for frequency. Okay, then the time interval corresponding to a phase angle of 90 degrees. So a phase angle of 90 degrees corresponds to time interval of 1/4 revolution. Okay, so we know one complete cycle is 10 millisecond. So 90, the phase angle of from here for it to turn and come to this at this point is 90 degrees. So if you want to find 90 degrees, so total you have 360 degrees for one complete cycle. So you need to divide 10 millisecond into 4. Okay, because 90 degrees of 4. But 90 times 4 is 360. Okay, so we can get from here, from this position, turn to this position, it only take 2.5 millisecond. So consequently, phasor EB2 lags 2.5 millisecond behind phasor EA1. So because earlier we can see EA1 reach first, then only EB2 starts. So EB2 is lags 2.5 millisecond behind EA1. Okay, so that's one example for you to understand. Okay, so power generator of a two-phase generator, power output. So we can connect like this. So the first winding is connected to one load. We call it as a phase A, and the second winding is connected to phase B. Okay, so two identical resistive loads are connected to phase A and B. So uh, current IA and IB will flow. So it will flow like this and like this. So IA and IB are in phase with EA1 and EB2 respectively. So you can see in this graph, IA is in line with EA1, IB is in line with EB2. So the current are 90 degrees out of phase with each other. So the angle is 90 degrees. You can see from here to here is 90 degrees. So the generator now produces a two-phase power output. So the generator produces two power waves. So this is wave 1 for phase A and this is phase 2 out of phase by 90 degrees. So when you combine it, uh, so you will get a constant power. So when the power is maximum, the resultant power is constant. You can see it's a constant power equal to the peak power Pm of one phase. The two generator does not vibrate and less noisy. So compared to a single phase, which is only depending on this, so we can have at times have power, at times no power, even though it happen in a faster rate. But when you have two phase, so it will generate a more stable and less noisy uh, electrical generation. Okay, so now we move to three phase. So three phase generator is something that we always hear. So similar like earlier. So earlier we saw for single phase generator or one phase generator is only having one winding. So A1 for two phase we saw it has A1 and B2. For three phase it has A1, B2 and C3. C3. So it has three. So earlier it was out of phase by 90 degrees. So now it is out of phase by 120 degrees. Okay, so it has three identical winding. So the winding are placed 120 degrees from each other. When the magnet rotates at constant speed, the voltage induced in the three windings have the same effective value. So earlier we only saw it has two. So now it has three. So E1, EB2 and EC3. So we can see it can have a waveform like this. At the moment the magnet as in figure, the only EA1 is at the maximum positive value. So here voltage EV2 will reach its positively peak after the rotor has turned through an angle 120. So at this angle under 20, so EB2 is maximum, then it will start. Here is the power output of a three-phase generator. The generator has three identical resistors. So generators, how it will get the it will output the power is through resistors. So it has three identical resistors. The arrangement requires 6 wires to deliver power to the individual. So you need 1, 2, 3, 4, 5, and 6. So you need 6 wires. So the resulting current IA, IB, and IC are in phase with the voltage EA1, EB2, and EC3. So it will produce E1, EB2 and EC3. Because the loads are identical, the current at the same effective value. So similarly, it has same value, just it is out of phase by 120 degrees. So the power peak in the three resistors does not occur at the same time due to phase angle between the voltage. So if, the electrical generation is actually it flicker very fast, but for us it look constant. So three phase will have better stability in the electrical generation. Okay, so you can see that the phase generator is connected uh, to a 20 ohm load resistor. If the effective voltage induced is 120 voltage, so we can see this is a three phase because it has three windings. So we need to find all this information. Okay, so P equals to E square R. So E is given effective voltage induced is 120. So 120 square divided by resistance is 20. So divided by 20. So power is 720. So the total power dissipated in the three phase load. So PT. So this is only for one phase. So we have three phase. So it's 3P. So 3 times 720, which is so total power dissipated is 2160 watt. So make sure you put the correct unit, which is watt. So the power is absolutely constant from instant to instant. Okay, so the third part. So the peak power dissipated in each resistor PM. So the peak voltage across one resistor is EM equals to square root of 2 E. So square root of 2 times E is 120. So 169.7. Okay, so the peak current in each resistor is IM equals to EM over R. So this is from the formula V equals to IR. So IEM will be calculated 169.7 divided by R is 20. Okay, so IM is 8.485 ampere. So the peak power in each resistor is the power, the formula is VI. So here, we use EM times IM. So 169.7 times 8.485 ampere. So it is equal to 1440 watt. Okay, so the ratio of PT to PM. So PT is 2160, PM is 1.1440. So 2160 divided by 1440. So the ratio of PT to PM is 1.5. Okay, so with this, I conclude for part 1. Thank you.